Hello guys, welcome to Silent Speaks YouTube channel. In this video, I want to revise graph theory in discrete mathematics for GATE 2024. So a graph is defined as set of vertices and set of edges. Each edge must be associated with an ordered pair of vertices. So we have to study self-loop, which means where the end vertices are same, then the edge is called self-loop. And we have to study for degree or valency. So number of edges incident on a vertex is called the degree of the vertex. Next, null graph. It is a set of isolated vertices. So this is the example of the null graph. So first of all, theorem 1. Sum of the degrees of all vertices is twice the number of edges. So this is the one of the important theorem. So you have to remember this. So theorem 2, number of odd degree vertices in a graph is even. So you also remember this point. Based on parallel edges and self-loop, graphs are divided into three types: simple graph, multigraph, and pseudograph. Theorem 3, maximum degree of a vertex in a simple graph with n vertices is n minus 1. So if there are n vertices, then the maximum degree for a vertex is n minus 1. And theorem 4 is number of edges in a simple graph with n vertices is nc2. Number of different graphs possible with n distinct vertices is 2 power n square minus n by 2. Number of different graphs possible with n distinct vertices and e edges. So n into n minus 1 by 2 CE. So degree sequence. If the degree sequence of a graph are written in increasing order or decreasing order, we call it as a degree sequence. Not all degree sequence forms graphs. So check it below vertices form a graph or not. So from the theorem 2, it is not satisfied as number of odd vertices is odd. So degree of vertices should be even. Degree of odd vertices. So it is odd. It says satisfy theorem 2, number of odd vertices is even. So maximum degree in a simple graph must be n minus 1 is equal to 4. But here maximum degree is 5. Okay. Howell-Hemke algorithm. So this algorithm is used for the degree sequence to find out the whether a graph is possible given the degree sequence. Theorem 5. In a simple graph, at least two vertices will have the same degree. Is not graphical. So consider a graph with n distinct vertices. But maximum degree possible is n minus 1. So theorem 6. Maximum degree in a simple graph G is denoted as delta of G. Minimum degree is So next one is type of graph, complete graph. Degree of every vertex is n minus 1. So the direct edge between every pair of vertices. Number of edges in a complete graph is n square minus n by 2. Regular graph, a graph in which degree of all vertices is same, called a regular graph. Every complete graph is regular, but not vice versa. If degree of all vertices is regular graph, then k, then we call it is a k regular graph. Cycle graph. Degree of all vertices is 2 in a cycle graph. Every Cn is a regular graph. Number of edges is equal to n. A wheel graph Wn is obtained by adding a vertex to C of n minus 1, which that is vertex is adjacent to all the vertices. So in wheel graph number of edges is 2 into n minus 1. Next one is line graph. Line graph for every cycle is also a cycle. Calculating number of edge in the line graph is given is page number 158. Bipartite graph. A graph in which vertices are divided into two sets V1 and V2 and all the edges in a graph such that number of two vertices of the same set are adjacent. Bipartite graph does not consist of odd length cycle. So this is also the one important point you have to remember. Each vertex in a set V1 is adjacent to the each vertex in a set V2. So it is a complete bipartite graph. Theorem B. Maximum number of edges possible in a bipartite graph is with n vertices is n square by 4. From the above observation, we can conclude that the maximum number of edges is obtained when vertices are equally divided into two parts. So thus number of edges is n square by 4. Star graph. It is complete bipartite graph with one vertex in one set and rest of the vertices in other set. Star graph is complete bipartite graph possible with n vertices and maximum number of edges. Complement graph. For a graph G, complement of G is a graph which contains all the edges which are not present in the G and does not contain all the edges present in G. So this is a complement graph. If the degree of a given vertex V is x in graph G, then the degree of the V in G dash is n minus 1 minus x. So consider a graph of degree sequence something here, and what is the degree of sequence of the complement graph? So you have to do subtraction for this. Consider the degree sequence. So this is also same. So all the types of graphs are completed. Isomorphic graph. Two graphs G1 and G2 are isomorphic to each other if they have same incident property or meeting property. So in isomorphic graph, same number of vertices, same number of edges and same degree sequence are there. So if these things are possible, then the two graphs are isomorphic to each other. But still the above graph are not isomorphic to each other because they don't satisfy the meeting property or incident properties. Thus, if two graphs are isomorphic to each other, they will have same number of vertices or edges or same degree of sequence. But reverse need not be true. So G1 and G2 are isomorphic to each other if they have 1:1 corresponding function between G1 and G2. So when two graphs are isomorphic to each other, it means they actually same graph with different representation. When asked if two graphs are isomorphic or not, check if both graphs have same cycles or not. Then go for checking their properties. So this is an important point you have to remember. First you have to check both the graphs have same cycles or not. And next, self-complement. It is a graph which is isomorphic to its own complement. It is clear that above two graphs are self-complement to each other. Self-complement graph is not possible with a graph of 6 vertices. Self-complement graph is not possible with a graph of 7 vertices. Thus, for a graph with n vertices, self-complement graph is possible 4 by n into n minus 1. 4 by n or 4 by n minus 1. C5 is the only cycle graph which is self-complement. C5 means I think it is complete graph, I think. So here is the question, what will be the total edges in the complement of star graph of 6 vertices? So this is the solution. Complement of star graph gives one isolated vertex and a complete graph k n minus 1. Consider graph vertices are represented as n minus 1 bit signal and two vertices are connected with each other. If they differ by 1 bit, then the number of edges in G, number of edges in G dash, and degree sequence of G and G dash n greater than or equals to 3. Given that the graph is represented by n bit signal, number of vertices is equal to 2 power n. Since number of ways we can write n bit numbers for a given n bit number such that they differ by 1 bit is n. Connectivity, consider below graph. It is an alternating sequence of vertices and edges. Means that is walk. Trail. It is an alternating sequence of vertices and edges. So you can take this as an example to remember this walk, path, and trail. For walk, it has repetition of vertices and repetition of edges. For tail, it is only have repetition of vertices, but not repetition of edges. For path, it does not repeat vertices and edges. Connected graph. For every two pair of vertices, there must be exits a path between them. So then it is a connected graph. So disconnected graph is the opposite. Disconnected graph consists of connected subparts called components. If G is connected, G dash may be connected or disconnected. Theorem 1. If G is disconnected, G dash is connected. For a graph G, either G or G dash will be connected. Range of edges for a connected graph. Minimum number of edges required to get a possibility to make a graph connected with n vertices is n minus 1. The connected graph with n minus 1 edges does not have a cycle. This graph is known as minimally connected graph. In this kind of graph, there will be a unique path between two pairs of vertices. This kind of graph is called a tree. Range of edges for a disconnected graph. So forest is a collection of trees. This number of edges in a forest of n vertices with k trees is n minus k. Cut edge or bridge. The edge whose removal from a connected graph makes the graph disconnected is called cut edge or bridge. So here E1 is the cut edge and here D is the cut edge. If a cut edge exists in a graph, then cut edge never belongs to any cycle. Cut vertex, cut point, or articulation point. The vertex whose removal from a connected graph makes the graph disconnected is called cut vertex. So the ends of a cut edge are cut vertices. So AB is the cut A and B or the cut vertices. For a graph with n greater than or equals to 3 vertices, if cut edge exists, then cut vertices exist. N vertices of cut edge. But reverse need not be true. Cut edge set. It is the set of edges whose removal of a connected graph makes the graph disconnected. Also, no subset of a cut set is a cut set. Edge connectivity or minimum cut. It is the minimum number of edges that are to be removed to make a graph disconnected graph. It is the size of the minimum cardinality cut size. The edge connectivity of the above graph is 2. So find the cut edge connectivity of the below graph. Having every edge belongs to a cycle and its edge connectivity cannot be 1. If you remove 6 5 and 4 5 edges, so we can make the graph disconnected. Cut vertex set. It is a set of vertices whose removal of a connected graph makes graph disconnected. Also, no subset of a cut set should be a cut vertex set. So if you remove 2 comma 5, it brings a cut vertex set, and also 3 vertex connectivity. It is the minimum number of vertices whose removal of makes the graph disconnected. Relation between the minimum degree and edge connectivity. Here BC and DC is the edge set. From the MO observation, we can conclude that minimum degree is greater than or less than or equals to 2. Relation between vertex connectivity and edge connectivity. So this is the relation. So coloring is nothing but we have to color the graph in such a way that no two adjacent vertices have the same color. So chromatic number, it is the minimum possible number of colors required to color the graph. So chromatic number of a cycle graph, it will be 2 if n is even, it will be 3 if n is odd. Chromatic number for a complete graph is n. Chromatic number of a bipartite graph is 2. Every bipartite graph is a two colorable and every two colorable graph is a bipartite graph. So this is also important to remember. Two colorable tree bipartite graph. Even length cycle, so it is also a bipartite graph. So a bow graph, this is a bipartite graph because it is a two colorable. So complement of a star graph is a combination of an isolated vertex and a complete graph. So chromatic number of a complement of a star graph is n minus 1. So next one, independent set. It is a set of non-adjacent vertices. So here A comma C, A comma C comma D, A C D F are called the independent sets because they are not independent to each other. So it is an independent set in which we can add any new element. It is called the maximal independent set. And independency number, it is the number of vertices present in the largest maximum independent set. So finding chromatic number and independence number of the below graph. So dominating set such that if we can take any vertex from V, either the vertex directly belongs to D or it adjacent belongs to D. So if you see clearly exclusive or one to other. So ABF is a dominating set. BE is a dominating set. is also a dominating set. To remove an element, all the adjacent vertices of that element must be present in the set, and adjacent vertices of that element are adjacent to some other vertex in the set. So minimal dominating set. The dominating set from which we cannot remove any element from the set such that it is still a dominating set. And this is the dominance number. Dominance number is always less than or equals to the independence number. Covering is a set of edges such that all vertices should incident on at least one edge. So 1 6 and 1 2, 6 5, 5 3, 5 4. It is the edge covering set. And these two also are examples for the edge covering set. So minimal covering set. It is a covering set from which we cannot remove any new elements. Covering number. It is the number of edges present in the smallest covering set. So for the above graph, covering set is equal to the covering number is equal to 3. So 1 6 1 2 5 3 5 4 1 6 5 4 2 3 1 6 5 4 2 3. Yes. Every perfect matching in is minimal covering set, but reverse need not be true. So vertex covering set. It is a set of vertices such that all the edges should incident on at least one vertex. Minimal vertex covering set. It is a vertex covering set from which we cannot remove any new vertices. Euler circuit. It is a closed trail that covers all the edges exactly once. So these are the important topic in this chapter. Euler circuit, Euler graph, Hamiltonian cycle and Hamiltonian graph. A graph is called Euler graph. The graph has Euler circuit. A graph is a Euler graph if degrees of all vertices are even. Open trail. It is a trail in which starting and ending vertices are different. Euler path or Euler line. It is a open trail which covers all the edges exactly once. A graph contains the Euler line if the graph contains exactly two odd vertices. Also, the Euler path starts at one odd vertices and ends at other odd vertex. Hamiltonian graph. Alternating sequence of vertices and edges in which vertices and edges are not repeated. So, Hamiltonian circuit is a closed path that cover all the vertices and exactly once. Hamiltonian graph, it is a graph which contains Hamiltonian circuit. Hamiltonian path, it is a open path that covers all the vertices exactly once. Every Hamiltonian circuit contains Hamiltonian path, but reverse need not be true. Every above graph contains Hamiltonian circuit and hence contains the Hamiltonian path too. So if you check this graph covering all edges, means it is closed trail and open trail we have to check. It is closed trail, it is Euler circuit, open trail, it is Euler line. It covering all vertices means we have to check closed path, Hamiltonian circuit. If it is open path, Hamiltonian path. Line graph of every Euler graph is also a Euler graph. Line graph of every Euler graph will always be an Hamiltonian graph and Euler graph. If G is a Euler graph, then L of G is both Euler and Hamiltonian graph.